So let me start by introducing James. James Caverlee is a professor at the Department of Computer Science and Engineering at Texas A&M University. He works in a wide range of topics related to IR recommender systems and social media and network information systems. He was the general co-chair of Wisdom 2020. I actually attended that conference, and I think that was the last time we met in person.
Yeah.
So it was a very nice conference, especially the barbecues that we had in the banquet. I really like that. And so he has been a senior program committee member of a lot of major venues like KDD, CIIR, SDM, Wisdom, and ICWS. So please join me by with a round of applause. Welcome James to UMass virtually.
Great, thank you. Thank you so much, Ahmed, for the very nice introduction. And thank you, everybody, for joining us today. And I also want to thank Jean for helping to organize. We had some emails back and forth. Everything went super smooth. I do have my chat window open. So for those of you who are joining via Zoom, I will keep an eye on chat. I've thought about maybe becoming a Twitch streamer. I feel like this is one of my few talents. So if you have questions, please throw them in the chat. I'd be happy to answer as we go along. And of course, in the audience there, please feel free to ask questions. Yeah, no, it's really exciting to be here and have an opportunity to talk about some of the work we've been doing in our group. Quick backgrounder. Yeah, so my research kind of touches on a lot of different topics. And so kind of historically, I've had one big thrust looking at social media and kind of web mining. And so we've done a lot of work there looking at location and geosocial characteristics in social media. And that's kind of one thread that I still have alive, and I have a lot of interest there. Another kind of thread that we've had over the years is looking at I call it information quality, but you can think about social spam, bots. This is related to misinformation, but also very practical attacks on review platforms. So we've done a lot of work in that space. And then there's sort of like a demarcation line here. In about 2015, I went on a sabbatical. And I think it's good for faculty every 5 or 6 years to kind of reassess what they're working on. And kind of coming out of that sabbatical, I picked up a couple of new threads that I've really been highly engaged in the last so many years. And so one of them, of course, is on recommender systems. And that'll be part of the discussion today. And then the other one is in terms of responsibility. And so you can think about this in terms of fairness and bias. But we've done a lot of work in this space in the context of recommenders, but I see a lot of opportunity to push it out beyond recommenders into a number of other application spaces. Okay, so let's get into the talk today. So I'm going to do two things. So I'm going to talk about what I think is one of our more exciting works on the recommender side, where we're going to look at these high order networks, or we'll look at hypergraphs. And then I'll talk about some of our work in this responsibility space, in particular around recommenders. I'll give you a brief summary of several projects. Of course, we have extra time. I can go a little bit deeper, but of course we can talk about that offline. And let me acknowledge gratefully support for this from Amazon, NSF, and some of the earlier work that we did in this space came out of some DARPA projects. Okay, so yeah, the first project is about improving recommender systems, and in particular in this context of these high order networks. Before even more acknowledgements, I forgot. So this first half of the talk is primarily due to work from one of my superstar PhD students, Jian Ling. She has defended and I think she started, but she'll be at Google Research certainly in the next few months. So she's done a really great job. I'm really proud of her. And then the last half of the talk will be emphasizing some work by my student Zoe, who's going to take an assistant professor position at George Mason starting next fall. And I wrote PhD 2022. He hasn't actually defended yet, but that's coming up in a few months. So I'll put a little star there that he's on the way out. But I really want to acknowledge their really great efforts. Okay, so now let's get into the first topic. So recommender systems, right? I'm assuming most of us are familiar with them. But the idea is what we're showing on the left-hand side is we see these many platforms where users are interacting with some some items. Typically, they could be movies, but they could be job postings. They could be news items, social media posts, et cetera, et cetera. And the idea is these users are interacting with different kinds of feedback. They're rating things, they're clicking things, they're reviewing, purchasing, they're maybe just viewing or dwelling on certain items. And the idea, right, is that a recommender system is trying to somehow build a model of user preference based on these activities, so that in the future time steps that we can make good, good guesses about what these users should be exposed to, or what kinds of items we should put in front of them. So, of course, when we think about our users, the preferences of our users are inherently dynamic. And when you think about that dynamism, right, it could be on a very short time scale. So, you're reading the first Harry Potter and you're kind of in this Harry Potter phase, but you could also think about these user preferences over longer periods of time. So here's sort of this notional idea, from a child to, sort of a tween, teenager into a young adult, and the preferences can change over time. And so the idea is, right, these models should be perceptive to both kind of these very short-term changes as well as these long-term changes to really have a deep understanding of our users. And so naturally, this leads to an area called sequential recommendation, where the idea is we're going to use those historic user item interactions, right? And the idea is basically on the right-hand side, right? We're trying to figure out, like, what is the next item that we should recommend to the user. And so what we're going to try to do here is, rather than treat users as static, which you see in a lot of work, I mean, not totally, but a lot of work will treat users as fairly static, is the idea is trying to build a dynamic preference model for our users, so we can capture, in this case, this user over their lifespan. So at any point, we're making more intelligent recommendations. Okay, that's kind of like the big setup. And so if you look at a lot of work in sequential recommender, the models are oftentimes, in various sort of methods, but are somehow trying to infer some dynamic user preference, typically by looking at the item representations that the user's been interacting with. So here you have some user B, looks like she's going to get married. And so she's been interacting with, sort of wedding related items, right? And then at the end, some iPhone. And so the idea is somehow trying to aggregate all of that and trying to figure out, what is this user interested in? Are they still in that kind of wedding planning mode, or are they sort of transitioned to a new mode? And in some way, kind of intelligently aggregating those items to figure out what is the user's preference at this point in time. Okay, so the big question, of course, is how are we going to model those interactions between a user and an item? And so here, what I'm showing you are three kind of, again, notional users, A, B, and C. And if you notice in the kind of in the middle there, we have this, there's this flower bouquet here. And if you look closely, right, it's the exact same one, right? And so naturally, right, you could, we could treat items statically, right? So each of these users has interacted with this one item. And so that's all we need to know. But of course, if you look kind of across, you'll notice that each of these users is interacting with this item in a different context, right? So the first user is looking at a mom and daughter necklace, a bracelet, and a mom side. So you can imagine this is some sort of Mother's Day, or a Mother's Day gift or something like this. The second one is interested in flowers, and this last one is some kind of like wedding theme. And so the point here is that the flower bouquet, right, like sort of the semantics of it, like what is its meaning in this context? It is different from each one. And naturally you can say, well, it's somehow correlated with the items around it, right? And this kind of motivates us to start thinking about how can we more intelligently how can we more intelligently model these items, right? So that we can more intelligently build this dynamic user preference models. So that leads us to this idea of moving from kind of traditional simple networks, kind of just nodes and edges, to a high order network, or in particular, hypergraphs, okay? So the big challenge here is that kind of from that example is that you can see that like the meaning of the item can change, right? And indeed it can change for different users. And so again, here's we're taking that same example, but kind of plotting it slightly differently. But you see there's a flower bouquet in the middle. And kind of this user A, right, is interested in weddings, right? But then here we see some user B is doing some kind of home decoration, right? And so the idea is sort of the meaning of the item is different for different users. However, you can also see that the meanings of items can change over time. And so what I show here on the left-hand side is an iPhone 8 that was a brand new, hot. It was like the hot new technology, along with a Nintendo Switch back in 2017. So you can imagine the iPhone 8 then was, a premium item, fresh, people who are sort of chasing the newest trends. It's something that they might be buying. But if you fast forward by 2 years, the idea now the iPhone 8 is no longer the hot new phone. It's more of a budget pick. And just to sort of get that across, we're grouping it here. Here's E is a budget consumer who's buying like the cheaper version of the Nintendo Switch and is maybe looking for not the newest iPhone, but kind of the older iPhone. Whereas up top, you'll notice, okay, here's an iPhone 11. This user is chasing kind of the latest tech. So the idea, right, is like it's these items, they change for different users, but they also change across time. And so naturally, we want to think about how we can treat these items. And so the intuition here, I think you should probably have it by now, it's pretty straightforward, is that basically we're going to try to model and understand like what these items mean by who's interacting with those, by those user interactions, but also looking at it in a short term. So the idea is we're going to somehow have to truncate the window at which we look at these interactions so that we're not kind of conflating interactions from 2017 with 2019 and kind of losing the idea that the iPhone has kind of fundamentally changed its meaning. Okay, so again, just kind of showing it here, right? You can see how over time, the iPhone 8 becomes a budget choice. Okay, so what kinds of correlations do we care about, right? So there's a couple of things that we care about here. So one is high order correlation. So that would be the idea that in any time period, a user may purchase multiple items, right? And so I think you can see where we're headed with the hypergraph is the idea is we want to be able to model all of those purchases kind of simultaneously. And so we want to say here is these users are purchasing multiple items. So we want to model that sort of high order relationship, but we also want to be able to do this multi-hop, right? So the multi-hop would be, the Switch was purchased by E, which is connected to user D via the iPhone to the AirPods Gen, which was also purchased by user B. So the idea is you can have these multiple hops that may give you some hints on the meaning of items as you kind of move along these kind of patterns of transactions, okay? So we have these two kinds of correlations, and that leads us to this idea of a hypergraph, okay? And so the idea of a hypergraph is just a generalization of a traditional graph. But the idea is that the hyper edge, it connects multiple nodes on a single edge. So in our notion here, what we're going to have is, each of those nodes, that's going to be an item, right? So you can see this is an item. And in this case, the edge, the hyper edge, and you can see in this case, right, like, this is a single hyper edge, but it's connecting 3 items. So those 3 items were purchased simultaneously by this user or within this time window. And so the idea is a single edge is connecting all of those items that the user has interacted with. And again, that the user has interacted with in this short time period. So somehow we have to get this notion of time into this, right? Because that's the key concept, which is when those edges exist connecting items, which exact interactions should make it into that hyper edge. Okay, so that leads us to this idea of HyperRec. It's a sequential hypergraphs for sequential recommendation. This was, again, work led by my student, Jian Ling. She has a follow-on work where she's looking at a slightly different topic of session-based recommendation. So if you're interested in the topic, I'll mainly focus on the work that we published in CIIR back in 2020. But there's a follow-on work at a conference in the following year, okay? So big picture, what we're trying to do is, again, model these sort of time-sensitive changes in meaning of items and embed that in some kind of sequential recommendation model, okay? And so at a high level, what you'll notice here is we have this notion of a sequential hypergraph. I'll explain that next. We're going to use that to build our dynamic user model that's up top. And then eventually we can put that all together to predict the preference of a user so we can make better recommendations based on what the user is really interested in at this moment in this sequence. Okay, So let's look at the first bit about all of this, right? The sequential hypergraph thing. So the big idea here is we're trying to generate these dynamic item representations, okay? And so if you look at the figure, this is one of these classic figures. It's like super complicated. I'm gonna try to break it down and make it sensible. But let's focus on here what we mean by a sequential hypergraph. So what we're looking at here is we're basically going to chunk our universe into these like windows. So we have like T1, T2, up to, let's say, Tn. And so you can imagine, you could define this sort of granularity. It's kind of application dependent. But again, like imagine, if you were looking at Amazon, for example, at a very coarse scale, this could be, all of January, all of February, up to December. And so the idea is you could chunk up all of the January transactions only live in this first sequential hypergraph, okay? And then at time 2, we only look at February. Now, of course, you could do this by week, by day. You can be a little, more granular. You can pull it back, again, kind of depending on the platform you're looking at. But the point is that in each of those chunks, so the idea is if we're just looking at January, we're going to then look at all of the user item interactions just in January. And we're going to then build what we call a short-term hypergraph that is going to reflect the relationships between all of these users and items in January. So the idea there is we're getting this kind of locality in terms of how those items were kind of co-purchased or co-interacted with. And the idea that's going to give us more kind of sense of what the item is all about. Coming back to kind of like our iPhone case, right? We want to make sure that we're focusing on the iPhone kind of in its different periods rather than kind of smoothing out across its entire lifetime. So in each one of these short-term hypergraphs, we're then going to be able to build a representation for items. So you'll notice then, like if in our case of the iPhone, we're going to have some iPhone representation here, here, here. So we're going to have different representations at different points in time based on, again, what falls out of this hypergraph, meaning who else has been purchasing it, what other items have been purchased around it, and so forth. Okay. So if you drill in on this sequential hypergraph, so again, we're just focusing on, let's say, January, right? So again, each of our nodes, that's an item, right? These are all different items. And the edges, again, they correspond to, this is a user, right? And this is a different user. So we have these items, right? In this case, this user purchased items 0, 1, and 2 simultaneously. And so basically what we're going to do is we'll then basically do like a convolution. At some point we'll do a convolution. But what we'll end up doing is basically passing the representation of each of the items to the edges, right? So the idea is sort of at the first step, the node passes representation to the user, and then the users back to the items, right? And so you can imagine this way, you can then pass evidence along these chains to update your representations for our users and our items, okay? Then the question is kind of like, how many layers do we do this for? And that's sort of an empirical question that we'll have to study in our experiments, okay? But the idea now is we now have like a representation for our users and our items at each kind of time window, okay? Now, if you pull back kind of to that figure before, so again, this is kind of like this first little bit here, like, let's say that's January, right? And let's say this is February. And so one of the things you have to be careful with, which is you can have some sparsity at each one of these hypergraphs. And so you want to be careful about which information passes along so that, so we basically build in a residual gating layer so that in this case, like whatever representation we have in January, we're just going to pass along sort of the important bits to the next layer, or excuse me, to the next time window, to February, and on and on and on down the road, okay? Now, so once we've done all of this, right? So the idea is now we have this representation for all of our, let me pull back so you can see now we get this dynamic item embedding, right? At each of our like January, February, each of our time slices, okay? Now we're going to go back and say, well, but how do we represent the users, right? Because we need to build the sort of dynamic model of our users. Because this is like super critical, right? We need to figure out what the dynamic user preference is. So what we're going to do is basically, it's pretty straightforward, I think. So basically we can take whatever the short-term user intent is, is basically just, look, we can say, which items have you interacted with recently? That's just the embeddings of the hyperedges. That's the user, right? So in this case, this is the user. What is their short-term user intent? It's just, based on the items that you've been interacting with recently, that gives us a model of what the user is. So then we can take the short-term user intent, right? We have the dynamic item embedding that came out of the sequential hypergraph. Sequential hypergraphs. We also keep a static item embedding. So this is, again, this is across all time periods. And we basically fuse all of those together to then get us a representation for the user item interaction at a particular timestamp, right? So each one of these, we can figure out the short-term user intent, the dynamic item embedding, some static item embedding, fuse all that together, and it gives us a model of the kind of the user item interaction at that particular point in time. Okay. And then, like a lot of works here, right? We then need to aggregate all those interactions because we need to put them all together to give us our singular dynamic user embedding. So we're going to use a self-attention layer to then aggregate all of those interactions. And then the output of all of that, right? That's going to give us our dynamic user preference representation. Okay. So putting all this together, right? So we basically use these sequential hypergraphs. They help us build models of items across time. We now have dynamic user preference. And so at the end of the day, we can say, what was the last item you interacted with? What is a static item embedding? Plus, what is your current preference? And you put all that together and you get your predicted score, right? So this is the way we're going to make our estimate or make our recommendations moving forward. Okay. All right. So put all that together. This is this HyperRec. There it is. Okay, sort of visually. So let's go look at some experiments and see what happens when we put this thing into practice. Okay. So we look at 3 different data sets. We have one of these Amazon data sets. We have Etsy. So we have a bunch of transactions from Etsy. Etsy, is like a handcrafted kind of home crafted store. And then Goodreads. Goodreads is like basically like a book sharing or kind of you can rate and review books and kind of form communities around books there. So we have a bunch of users, we have a bunch of items, we have these interactions, right? And so the note here, we have a couple of these are more like e-commerce. Goodreads is not a commerce site. It's a pure, at least historically, it's been a pure kind of information sharing platform. And so basically what we set it up is we're going to go basically build our models, and then we're going to do this in we're going to do a cutting timestamp, where basically we're then going to make our predictions on the unseen future interactions. Okay, so that's this leave one out setting, right? So we use a bunch of standard metrics. We use hit rate at K, NDCG, MRR, and we're going to measure that at K equals 1 and K equals 5. Okay. So we look at a bunch of baselines. Remember, this paper was from we published this in 2020. So we do a bunch of classic sequential recommenders. There's like most popular, there's transrec, GRU for rec, this TCN from the previous year's wisdom. We also look at a bunch of attention-based recommendation frameworks. And you can see kind of the list here, SASRec, BERT for rec, and a bunch of others. And we put them all together and we run a bunch of experiments. And here's, let's see what we get here is, again, so this is like NDCG at 1 and hit at 1 for our 3 different data sets. And as you walk across, we get some really nice results. So we're really, really kind of excited that this kind of hypergraph approach we think is kind of like a nice way to model and gives us sort of really, really nice results in this case. Now, I think what's kind of interesting is if you look more closely, you see there is quite a there's quite a difference in the sort of the absolute scores that fall out here. So you'll see, for example, like like if you just look at like Etsy, for example, I don't know, let's just take like here. Sorry, if you look at just Etsy, if you just look at the sort of the magnitude of the scores, right? Like 59 versus 22 versus 46. So, I mean, there's a pretty wide variability across these different platforms. I mean, presumably that's a function of kind of the density of these networks and the kinds of platforms we're looking at. But as a result, you'll notice kind of the Etsy scores start out higher, and so we kind of squeeze out like a relatively smaller improvements. But the other ones where we're kind of starting from, at least for Amazon, we're starting from a lower spot, we're getting a nicer improvement. So this is kind of fun result, kind of exciting. I mentioned before we have a different number of these hypergraph convolutions, like kind of like how many hops out do you want to go? And that's the idea, is like how much of sort of this sort of multi-hop evidence do you want to incorporate back into your representations? And what I think is kind of interesting, right, is that like for all, be careful on the axes. You can notice, I'm not saying it's cheating, but you'll notice the scale is quite small. But the idea here is that in every case, right, moving over from one, you do see an improvement. It seems like there may be a saturation that may vary by the different platforms. So you can see Amazon, this is at 2, maybe 2 to 4. Again, Etsy is 2 and 3. Goodreads takes a little bit longer, up to 4. So I think it's kind of interesting, and something we're trying to figure out, like what is it about these different platforms in terms of kind of their structure, and why we're seeing this, because we don't have a good answer for that right now. And of course, we do some ablation, and there's more of this in the paper that I can refer you to. We do a bunch of ablations, and I'm not going to walk through all of this, but there's a bunch of design choices, obviously, right? It's like, why did you have that static item embedding? What if you get rid of it? Or what if you only use a static item embedding? What if you throw out that residual gating? What if you replace the hypergraph with like a simpler traditional graph? And so, for example, if you get rid of the hypergraph itself, you'll see like kind of a pretty big drop. And you can kind of walk through and see. So this is sort of a motivation for why we think each of these pieces is significant to the ultimate performance of the model. But in particular, the hypergraph itself, in terms of its simultaneity of being able to model those interactions, I think is pretty important, pretty cool. Okay. All right, folks, we are cooking. Thank you all for your attention. Let me just summarize the first half of the talk, which is basically the sequential recommendation task and looking at hypergraphs. And so to me, what's most interesting about this is really thinking about kind of the dynamic representations in the context of sequential recommendation. So I think there's a lot of ways we can continue to improve this. But to me, this sort of bringing in the sequential hypergraph is a really kind of a nice way to begin looking at this problem. We propose this way to incorporate these sequential hypergraphs to model the short-term correlations into this overall HyperRec model structure. And we saw some nice experimental results, which we find to be pretty encouraging. We can see that there are some differences, and so that's something we're trying to figure out. Like, again, how can we squeeze out more, and kind of what are the fundamental differences between these different platforms? Okay, cool. That's kind of the first half. So let's take a left turn here for a moment, and I'm going to present some work. Again, we're calling from the beginning of the talk. This is work primarily led by my student Zoe Zhu, looking at topics around fairness and bias, and in particular around recommendation. But when I've been thinking about this problem, I've been thinking about it more as responsibility is kind of a hot topic, but thinking about it more broadly beyond just recommenders, in terms of kind of these AI-powered user-centered systems. Okay. And so when you think about recommenders, like all that I've just been talking about, right, we kind of view these as like an example of an AI-powered user-centered system. And so you can imagine there's lots of these other spaces that I think have some overlap. It's like clinical decision support, e-learning, chatbots, and the unifying. Maybe this is obvious, but to me, I had to really think about this for a while. But the thing that sort of brings these all together to me is, you're basically seeing lots and lots of kind of this, I don't want to say homogenization, but kind of a lot of convergence to kind of these machine learning, deep learning, data mining techniques, like under the hood for a lot of these different platforms that are then, of course, based off of some kind of user-generated interaction feedback. So again, like in the context of our recommenders, right, it's clicks, it's ratings, like in a chat, it could be a conversation reply. In an e-learning system, it could be some other kind of feedback. But the idea is there's this feedback coming back into the system, which is then being used to then update the models. And so you kind of have this nice loop that's happening. That then the model itself is hopefully providing some high quality user-centered services. Okay. So to me, this is like really exciting. I think it's an exciting direction to go in, but of course, we know there are lots of risk and harms around these kinds of systems, right? And so I show a bunch of examples here. I'm sure you've seen, or many of us have experienced these kinds of problems. So the first example is about bias against women in job hunting. So basically a model learning some very superficial aspects of resumes based on some historically biased data, and then queuing in on these sort of irrelevant, or let's say not irrelevant, but like aspects of a resume that should not be considered negative, but that because the model is sort of only working on sort of the surface level, is then ending up with this sort of negative result and being biased against women. Many other examples you can find in terms of like exposing inappropriate content in video streaming. There's a recent example of some of you have seen this, right? A chat bot telling a kid to, I think, put a fork into into an outlet, and other kinds of problems that can fall out of this. So to me, sort of this responsibility in the system. There's the ACM Fact Conference, and you're seeing more and more kind of interest and excitement around these topics around fairness, accountability, transparency. Okay, so we've been thinking a lot about this notion of responsibility. In terms of how do we sort of identify, understand, analyze, potentially address. So can we kind of debias, or can we make these algorithms more fair? And so the hope here is, of course, to provide these fair, unbiased, accountable, and trustworthy services. So kind of broadly, this is kind of where my head is right now. To me, it's like too big of a topic to just tackle head on. So we've been looking at it in the context of recommenders, because again, first half of the talk was about recommenders, and you'll notice we very much are emphasizing, precision-like metrics, sort of NDCG and MRR, and we're really going to optimize on kind of the utility of the model and so forth. And in all of that work, we weren't thinking about or talking about notions of fairness or accountability. And so what we've been doing for the last few years in my group is really going back to some of the fundamental assumptions underneath a bunch of these recommender models, and trying to more deeply understand them from the context of responsibility. So let's look at the pipeline of a traditional recommender, right? So the idea, we have a model. This could be a sequential hypergraph. It could be whatever your favorite model is. And we use that to then serve to our users. Our users are going to then interact, right? They're going to click, rate, dwell, view, et cetera. Somehow they interact with us. We're then going to take all that interaction feedback, feed it back into the model, right? Typically to update the model, we may retrain it, and then we go deploy a new version of the model. And so you have this nice cycle, which we'd like to be kind of a virtuous circle, but of course there can be problems. And then at some point, at some point we may then go evaluate, kind of the quality of whatever it is we've done, right? So you can imagine this loop kind of continuously going around and around and around. So we've been looking at kind of different aspects of this. And so it turns out kind of each component, there's an opportunity for bias and unfairness to enter into the platform. So the first thing we've been looking at is data bias, right? And so if you consider, like in this case, that interaction data, if it's biased to begin with, right? If we feed it into a model, even if the model is sort of agnostic to whatever, it could then preserve that bias, potentially amplify the bias, and continue it around, right? If you can remember, there's a bunch of work looking at, word embeddings, right? And so the idea is, if you train, word to vec or whatever model on some historically biased, or let's say historic documents that have a bias in them, of course, it's naturally going to show up in those embeddings. And so the same idea is here in terms of recommenders, is that if the bias is coming in, the model can then, again, preserve or even exacerbate it. And so just to give you a flavor of what that's all about, we've been thinking about how do you decouple, in this case, the exposure bias from the observed interaction data so that you can learn the true relevance. So what I'm showing you here is, this again, this may be obvious to some of you. It took me a long time to get my head around all of this, but the idea, is very natural. It's like, the actual interactions that we observe, right? The whole idea is they're a function of the things that we really like, but also the things that we were exposed to, right? So the point is, if you were never exposed to something, you have no opportunity to, click on it or view it. And so, right, by not clicking on something you never saw, we don't have a true model of like the things that you really like. And so basically we've been thinking about this problem, this sort of selection bias or exposure bias, like which things are being exposed to our users, and then how does that then lead to potentially exacerbating that problem. And so you can think about this from the context of, like a not very popular item that a user may really like, doesn't get exposed, and by virtue of not being exposed, it's even less likely to be exposed in the future. And so then again, it kind of squeezes out the opportunity for these lower popular items to then get any kind of purchase on the platform. So that's kind of the first time, just giving the flavor of this. The second issue is around algorithmic bias. And so this is like a big deal. Of course, this is the idea is that the algorithm itself, regardless of the data coming in, but the algorithm itself may be inserting or amplifying bias, okay? So we've done a number of works in this space. But the main idea here is, right, you have some, you can imagine you have some training data that comes in, you train your model, but then when you actually go serve the model, or when you're on the prediction side, we tend to intensify the distribution skewness that was already present, in the training data. So this sort of exacerbation. I'm going to, because I was just watching my time here, I'm going to hop in and show you a little bit more about this. Just 1 second. I got to figure out the organization of these. Who put these slides together? Oh, I did. Okay. Yeah. So let me show you a little bit more about this. This kind of algorithmic bias. So this is a problem we've been looking at in the context of mainstream bias, and this was just at Wisdom 22. Yeah, the one that just happened. Also, just to call back to Wisdom 2020, yeah, that was the one in Houston, and that was the very last in-person conference I went to. I think it's the very last in-person conference a lot of people went to. I think we had no idea that was going to be it. Time really flies. It was a lot of fun. It's hard to believe it's been over 2 years since all that. Geez. Okay, so this work is about mainstream bias. Okay. And so this is, if you think about this problem, this is, the idea here is you have like niche users may be sort of penalized by the recommender. So what I'm showing you here, this is from, I think, from Movie Lens, and you can imagine here, it's like you have kind of these core users in the middle, and they love blockbuster movies, but then you have some quote unquote oddballs here, sort of niche users. They like award-winning films, or this user likes classic silent films. And if you actually go look across a number of data sets and across a number of different traditional recommendation models, what you'll end up finding is that these kind of oddball users, these niche users, end up being essentially kind of penalized by the model. And so these are actual like NDCG results that you find on this Movie Lens data set. I think this is using I forget which model this is, maybe a VAE, but the idea is like these niche users do really poorly if you're just using like a traditional model, right? Because basically what's happening is the model is overemphasizing the interactions from the mainstream users to the detriment of these niche users. And so we perceive this as a kind of bias, right, in terms of mainstream bias. And so then naturally the question is like, is this a real problem? And then of course, can we somehow make life better for these niche users? And so what we've done in this work is, one is just we have to identify, what do we mean by mainstream? What does it mean to be a mainstream user? And then secondly, can we then improve the recommendation utility for those niche users? And here's the trick, right? You'd like to help them without necessarily punishing the mainstream users. Because if you come back here, right, like if we could improve these to here, that would be great. But if we have to penalize everyone down in the aggregate, that may actually be a really, really bad outcome. So to be very careful, right? So the idea is we want to raise the lowers while keeping the ones who are already high pretty high. And it turns out that can be pretty tricky, especially if you're trying to deploy kind of like a singular model, right? So you can imagine kind of adding some sort of regularization term that would kind of penalize the mainstream users and improving these niche users. But in the aggregate, kind of the overall like utility of the system is going to go down. So you have to be very, very careful in how you structure this kind of stuff. So you can kind of watching the time here. I'm not going to give you all the details about how this works. But basically, we use some traditional outlier detection models to find these niche users. And then we propose what we call a local fine-tuning model to try to help us overcome this mainstream bias. And so I'll just give you a flavor of what we did. So we used kind of traditional and a more recent outlier detection model, which is basically saying, if you look at kind of the user item interaction space, who are kind of on the periphery, who are the outliers? And then we'll go call those we'll score them as being outside of the mainstream, okay? And because we're not so concerned with trying to build the perfect way to do this, we tried a bunch just to see if there was a difference. Like, in other words, if we try different outlier detection models, do they find different niche users? And so we ended up doing this is data from Movie Lens. But what I'm showing you here is kind of different mainstream levels. So basically what we do is we can then score all of the users based on like how much of an outlier they are. So the idea is like, these are our mainstream and these are our extreme niche users. And then we have, this is the 5 buckets. So it's like the lowest 20%, the highest 20%. We have kind of buckets of 20%. And so what I'm showing you here is the NDCG for those different buckets, right? And this is using a state-of-the-art, this is a variational autoencoder model we were using. But what you'll notice, right, is, just like I showed in kind of the sort of example figure at the beginning, is kind of regardless of how you define mainstreamness. So each of these rows is a different way to kind of define our mainstreamness. And the big takeaway is, this number is much bigger than this number, right? So that's the idea, is those mainstream users are receiving much higher utility than these niche users. You can see it's like these are like even double, right? It's like 2x, or even more than 2x in terms of the quality of the results or of the recommendations that they're receiving. So to us, it's a big, big problem. Okay, so the question is, how do we overcome this, right? And so this is this idea of, when we first thought about it, we thought like, let's build, the kind of the one model to rule them all. But again, it has this problem about how do you balance you want to have high overall utility while sort of maximizing these different buckets. And it turns out we found it to be really, really difficult to do, where we could kind of raise the lower boats, but we would end up depressing the top ones. So instead, we took this idea of what's called local fine tuning. Okay, and actually, my theta is quite small. Okay, but the idea is basically you can train the single model with all of your data. Okay, so now you have kind of a baseline model for serving your recommendations. And then what we're going to do, though, is for all of our users, we can then go fetch like a neighborhood around those around those users. Okay, and then we can basically then go back and fine tune the base model, basically update the parameters of the model by considering the neighborhoods around the individual users. So you end up cooking up a bunch of these local models, right? So what you're going to end up doing is trading off like the one model for lots of locally fine-tuned models. But the idea is like the heavyweight training you can do back here at the front. And then the idea is this sort of fine tuning, this is relatively lightweight, right? So this is kind of heavyweight up front to train the models, and then some lightweight fine tuning to kind of optimize for the different kinds of users, like the different kinds of niche users, okay? And so we do all of that. Here are the results. Again, I switched out the data sets. This is Yelp. And these are a bunch of, this is a bunch of baselines. This is us. This is our local fine tuning model. And so, right, this is the overall NDCG, right? But then if you look at the individual subgroups, right? So what's nice about this, like this is like a, let's say these are kind of variations. Let's say if you look at just like the VAE, right, we're able to pull up those niche users. But the other thing is, notice at the high end, right, we're able to increase it slightly as well. The key is we definitely don't punish it. So you'll notice that the absolute value is quite small. It's only 2% here. But the good news is for our more niche users, we're getting a much bigger improvement. Okay. And so we're pretty excited by this because it's allowing us to basically preserve the utility for those mainstream users while raising up our niche users. Okay. Yeah. So let me jump back. Cool. Yeah. So where were we, right? We were talking about algorithmic bias. And so I did this kind of deep dive into this wisdom work looking at the mainstream versus niche. But if you continue that loop, there's also a fairness issue, which is in the outputs that were being served to users, are they fair or not, regardless of what the data bias is or the algorithmic bias. And so the question here is, how do you fairly recommend different items or even different item groups to users? And so the idea here is, and again, I'm not going to go into any technical details, but we've done a lot of different works in this space as well. And so, for example, if you consider like a warm start recommender, so it's been up and running for a while, you build your model, and a lot of people have figured out, well, how do we emphasize fairness kind of once we're at the warm start cycle? And so indeed, we had some work a number of years ago where we tried to do exactly this problem, right? So we had this thing called fairness-aware recommendation, where basically we said like there was some kind of skewed historic interactions. And so this could be like some gender-based bias situation. And the idea is we're sort of trying to extract out this sort of gender component to end up giving a more fair recommendation, okay? But all of this is in the context of a warm start recommender. We already have lots of feedback and the users have been using the system and all this kind of stuff. So you have lots of historic interactions to use. So we actually had some work last year looking at cold start or fairness for new items. And to me, this is kind of a fun topic because it seems almost counterintuitive. What does it mean for a new item to be sort of unfairly recommended? What does that even mean? And so it turns out what's happening is if you look at kind of in the literature, a lot of these cold start models, these are all machine learned models now. But basically what they do is they try to do some transfer from the warm start representations back to the cold items. And so it's kind of the sneaky case where if there's bias here, it sort of sneakily gets propagated back to the cold start. And so to me, this is sort of a kind of a neat kind of counterintuitive thing where it's like, oh, like brand new items can actually be treated quite differently because the underlying models many times are inheriting bias from the warm start scenario. So it was kind of interesting, I thought. It was like not at all obvious to me that should happen, but it turns out it's quite an interesting problem. Okay, folks, you've been very patient with me. Yeah, so basically just two halves to the talk, right? First half, I talked about sequential hypergraphs and ways that we can improve recommendation, in this case, sequential recommendation. Second half is more of a high-level summary. I'd be happy to talk offline or later on about more details about the different projects, but we have a lot of stuff going on in there. And so kind of where we're headed. Oh, we have a good question. I'll come to that. So where we're headed is basically, I still have this bias and recommendation topic. I know like Professor Zamani and other folks there are doing really exciting work around like conversational information seeking. So I'm really curious about kind of how do you bridge those two topics, right? Kind of conversation plus fairness and bias. To me, this is kind of interesting area. And sort of technical approaches, we have a bunch of other ideas. We have some meta learning stuff we're working on. And the other thing I mentioned, I don't know if you were here at the very beginning, but what am I really working on next? Like I took that sabbatical many years ago. I'm kind of at that same point now. I'm trying to figure out what are the exciting new topics to work on. So I'm really curious to hear what folks have to say here. So with that, thank you very much. I think we're kind of low on time. I'm happy to take questions. In fact, I have a question in the chat, so I'll read it out to you. This is from Jeremy. He says, it's about the interaction and feedback. He says, you mentioned the feedback comes in the form of like clicks and rates and dwells, and many of these are implicit. Might not some of the true relevance come from the ability of the user to give explicit negative feedback? How much of the solution to the problem should be algorithm-based versus UX-based? Oh, yeah, this is a really, really great question. Yeah, I think you're kind of hitting at some of the hearts of the design of these systems over the years, right? Which is, we know like from explicit ratings and stuff that explicit ratings, like 1, 2, 3, 4, 5, or even thumbs up, thumbs down, those don't always reflect people's actual behavior. And the other issue is, right, it's much sparser than the implicit stuff. So I would say there's a big movement towards, can we do as much as we can with implicit? Because it just tends to be, we have so much of it relative to the other. I think the other point though is about how do you pull out explicit negative feedback? And so to me, that's like, I think that's a really interesting problem. And I think it's one that we don't know the answer. We have some partial evidence that people don't actually at scale give lots of explicit negative feedback. But if we could do a better job of that, that would certainly be a really rich signal for our models. So for certain, that's a really interesting point. Thank you.
Great. Thanks, James, for the very interesting talk. Is there any questions from the audience here or from the remote audience? Okay. Okay, let me turn the lift system on.
Hi, James. Can you hear me?
I can hear you just great. Yeah.
This is James. I'm curious about the outlier detection stuff you talked about in the fairness area, because it seems to me that one of the problems with a lot of fairness and equity issues is that we don't really know when we're being unfair until after the fact, and someone points it out. I mean, there are protected classes that are easier to find, but do you think the outlier process has a chance of finding other types of niche groups? I mean, you're a very specific one that you were talking about today.
Yeah. I have the question. Yeah. So this is a really great question. So the impetus of this was I think exactly to your original point was we had read a paper and we were thinking a lot about fairness without access to demographic properties. Right. So like for GDPR, and there's lots of other issues where you just don't know the protected attributes, but you'd still like to provide some kind of like fair method or fair result. And so that got us thinking about, could we somehow define fairness, not in terms of the users, but flip it around and look at it from the item side. And so the idea there was, if we could somehow exploit the item side to understand our how users are kind of grouped, then even if we didn't know anything about our users, if it's a protected class or whatnot, it would be some way that we could begin to kind of segment them and understand, are they receiving some kinds of disparate, unequal outcomes or some sort of disparate treatment? And so that's what motivated this mainstream bit, because we were trying to think about a way to kind of operationalize that idea. But I think kind of moving forward, I think you have a good point, which is like, how do we then generalize that out to other kinds of issues? Okay, number one. And number two, the kind of this point, which is we don't want to be dummies. And it's more after the fact someone says, yeah, but this group was discriminated against and you didn't know about it. What we're trying to do is trying to do that from this item modeling side, if that makes sense. To me, it's like a really, really hard problem. And it's just something that we're just scratching on. But yeah, that's something we're definitely thinking about a lot. Yeah.
Thanks.
Okay, any other questions? So let me ask one question actually. So I really like this mainstream bias problem that you talked about, which also remind me of the problems we have in the search engines for head queries, torso queries, and tail queries. So one question I have is, when you separate these data to subgroups, like by, for example, 20% of users for the mainstream and 20% for like the ones that are your niche users, how sparse the data is for any of these subgroups? For example, we see a lot of like the performance differences a lot. So I'm wondering if this comes from like cold start users that are in the niche group, or it's like just because of this mainstream bias.
Yeah, okay. I don't recall how we treated our cold start folks. Because that is an issue that we've had. We have, I'm trying to check back in the paper to see. Let me kind of punt on trying to answer it in the context of the mainstream. But I will say we have a different project where we're looking at a similar thing. We're looking at some popularity bias problem. And so it's related to mainstream, right? But it's the idea of like the more popular items are being recommended more than the less popular items. But it's kind of a similar kind of skewed distribution. And what we have noticed there is that there is a big, what sometimes people call popularity bias is kind of a conflation of low popular items not being sort of treated as well as the popular items, but kind of a sort of negligent treatment of the zero feedback items. Like, in other words, just because you're a new item doesn't mean you're necessarily at the bottom of the distribution, really, right? We don't know where you should be because you haven't been exposed yet. So kind of in that kind of related space, we have seen this issue where if you conflate the two, right, like low popular and fresh or new items, that's not the right way to do it. You should decouple those. And that's something we've been thinking about in a different direction. Yeah.
That makes a lot of sense. Thank you. Any last minute questions?
If you don't have a question, I have a announcement.
Sure, go ahead.
So thanks everybody for coming. I know the hiring season is ending, but Texas A&M is growing. People we're hiring, we will be hiring, we have been hiring like crazy. So if you have any outstanding students in the next cycle, please have them get in touch. So always looking for good people. Thank you.
Cool.
Shameless plug.
Okay, great. Thanks a lot again for the very nice talk. I really enjoyed it. So let's thank James for